Good afternoon, everybody, and welcome to this IABSE webinar supported by COE on carbon management in bridges. How low can we go? Thank you very much for attending. There are people dribbling in, and I'm sure there'll be more as we over the next few minutes. I'm just going to give a brief introduction to what's going to happen today. And a few notes about IABSE itself. IABSE is the International Association of Bridge and Structural Engineers, and today's topic is really focusing on our role in the climate emergency. IABSE is headquartered in Switzerland. It's an international organisation, as the name suggests, but Cameron and I are both members of the British group, so I'm sure we have lots of members from the UK, but hopefully all the way around the world listening into this talk today. While I have you captive and your attention focused, I'm going to talk briefly about the IABSE Symposium in Manchester, which is coming up on the 10th and 12th of April in 2024. We are currently accepting abstracts, and the abstract deadline is on the 31st of July 2023. And it's a really absolute topic for today's audience. We will be discussing construction's role for a world in emergency. And I'm sure you agree, a vital thing to be addressing, and as Cameron will talk today, there are ways and means of us as engineers and designers of starting to address some of these issues. The abstracts are invited on the following topics: designing and building for net zero, the regeneration, rehabilitation and adaptation of existing structures, design for longevity, reducing waste, smart structures, and then the essential value of competence, professionalism and ethics, which is a really interesting sub-theme within this, how we as engineers and what our ethical and professional responsibilities are around the world in emergency. As I said, abstract deadline on the 31st of July, so please consider getting your abstracts in and joining us in Manchester. More details about this and many other events on our website at www.iabse.org. I'll also take a minute to just note that registrations for the IABSE event in New Delhi are open, and abstracts submissions for the IABSE conference in San Jose are also open. So if you're interested in those conferences, please approach those. The British group are running several events over the next 6 months. Further details of those, of course, on the website, but I'll just pick up that the Future of Design conference is making a reappearance in London at the end of September, and more details about that will be announced soon. So it's my great delight really to invite to announce Cameron Archer-Jones as today's speaker. Cameron's an associate at COE and an expert really in bridge carbon management. He's one of the founders of the Net Zero Bridge Group and the author, along with one of his former colleagues, of the Structural Carbon Rating Scheme for Bridges, or SCORBS, which has given the UK market a measurable and articulatable value for bridges when it comes to carbon rating, and it's becoming the norm on a lot of projects that we certainly work on. As I mentioned, COE are sponsoring, and we have 300 registrations today. I see that we're not quite at that number. We're getting on for a large number of people on this call, so it's obviously a topic that's piqued everybody's interest. In terms of how things will work today, Cameron's going to give a talk for about 40 minutes, followed by Q&A. If you are interested in asking questions, and I hope you are, because we'll leave time for about 20 minutes worth of questions at the end. Please put the questions in the Q&A with your name and company, and I'll raise those with Cameron at the end, and hopefully we can get a good discussion going. So without further ado, I'm going to hand over to Cameron to kick off.
Thank you very much. Let me just get this fired up. Okay. Can you see that all right, David? Great. So yeah, thank you very much for the introduction, David. So my name is Cameron Archie-Jones, work for Kobe based in the London office. Have been working in bridge design, bridge assessment for just over 10 years or so as a design consultant. And the last 3 or 4 years have increasingly had very much a sort of carbon focus, really responding to some of the big challenges that our industry faces. So within this presentation, I hope this afternoon to give everyone a bit of a flavour of where we're at, an extension to where within the Net Zero Bridges group, where we're currently at, and then sort of invite to see how people can contribute. So the agenda that I'll sort of step through by way of the sort of formal part of the presentation, I've broken into 3 sections. So starting off with calculating carbon in bridges. Once you have that, that's obviously a fundamental ingredient to managing carbon in bridges. And then lastly, how low can we go? And I've sort of purposefully gone for the limbo analogy, you know, hinting that it can be uncomfortable to get as low as possible. But let's see how we go when we get there. So the first topic, I guess, is, as I say, the fundamental ingredient before we can start to think about managing things. We need to have sight of what it is that we're trying to manage. So with the increased focus that we have on this within our projects, we obviously need to make sure we're doing it fairly and consistently, to then sort of see if we're genuinely improving and if options are better than one another. So the next few slides I'm going to present is a combination of COBE input material, but that overlaps with what I'm sure everyone else is doing. And certainly within the Net Zero Bridges group, I know that it's what other groups and organizations are doing. And within that, we have a working group which I'm involved in, setting out, you know, how to calculate carbon in bridges fairly and consistently. And I'll give a little reference to a guide that we've put out. But then the extension being, what can we then do with it? So just by way of sort of one slide, really to summarize what I'm talking about, I'm not going to go into, I guess, a huge amount of the background detail on carbon calculations, but we'll leave that for references for people to follow up with outside. But to give that sort of broad overview, starting at the top left of this slide, the material manufacture and processes and energy use, they then lead to greenhouse gases. In a life cycle assessment framework, or LCA framework, which is the sort of formal process underneath which this sits, the indicator that then leads to is global warming potential, the unit of measure of which is carbon dioxide equivalents, or carbon for short. When we start to look at our projects with our sort of engineering hats on, the easy or most obvious part that we can influence is the upfront carbon, which I've pulled out from the full set here. And this you may have heard of before as well, referred to as sort of cradle to end of construction. So that covers material manufacture, transport to site, and construction activities and wastage on site. When we're doing a carbon calculation, and the ones that I'll present for a range of COBE projects, that is carried out by sort of subdividing the bridge into components with a sort of unique background material and or process associated. Then taking the quantity from the design, multiplying it by an emission factor, gives you the carbon for that component, and then rinse and repeat across the whole bridge. And then the sort of emission factor scope that you're choosing is then linked with the life cycle scope. But then you sum all those across the bridge, and then you end up with your total project carbon emission. And when we're talking about bridges, we're generally talking in tons of carbon. So quite different to what you might be familiar with in a personal sense. And then that link with the personal, you know, our sort of personal lives, there'd be, I guess, plenty of people on the call familiar with metrics that they're used to and what they like to compare to when they start looking at these sorts of numbers, because it can be sort of not as tangible, just seeing a carbon dioxide equivalent. The one that I tend to refer back to is that the sort of average annual carbon footprint of someone in the UK is sort of 10 to 12 tonnes per annum. So that's normally the number I have in my head when thinking about this sort of calculations. So then how does that sit within the broader life cycle framework? So I touched on briefly that it's part of this life cycle assessment framework. Just here, again, I won't go into a huge amount of detail, but this here is the breakdown of life cycle modules. And we tend to use this terminology, or I use this terminology quite a lot when talking about A1 to 5 or Module B associated emissions. So the before use stage, or A1 to 5, is what we were looking at the previous slide and highlighted in the blue box. The next most relevant part, and increasingly becoming more relevant, is then in the use stage, when we will generally be involved as sort of structural civil engineers, is then linked to the maintenance, repair, replacement, and refurbishment. So that's that B2 to B5 in the purple box. And then the other one, which will generally not be within our direct control, but we certainly can influence and need to be sort of cognizant that it's there and can be very, very significant, is the one in the green box. So the user's utilization of infrastructure, B9, in other words. And I've got a slide within the session to sort of pull that out and really tease out what we mean by that. So that's the life cycle side. So when we talk about life cycle or a calculation, we'll have a life cycle scope. It'll be broken down into these sorts of packets, and it should be, we will clearly say if it's A1 to 5 or if it's whole life or whatever it may be. Then looking at the bridge or the asset. What I've presented here is a table that we've settled on within that working group, within the Net Zero Bridges group, for the minimum components of a bridge that should be included within a carbon assessment when using it to compare against another bridge. And that might be one within your own organization, or more importantly, when comparing outside organizations or comparing it to a rating system, like the rating system that David mentioned at the beginning, and I'll get to within this presentation. So graphically, what does that mean? Looking over to the right, that's everything from the foundations all the way up to the top of the structure, but it also includes the ancillaries on the structure. So as bridge engineers, again, we may not have direct control, but we will influence the surfacing, in this case here, if it's direct fix or if it's ballast. So it does include, or the assessment should include, the rails and the track slab and the infill layer in this example. And as well, sort of architectural parapets and things that aren't necessarily strictly part of the structure, but they're part of what we can influence and should be considering. So then the last one really on the details is to refer anyone that wants to get a bit more understanding of these carbon calculations, how to do them, to look into these 4 references I've got here. Definitely would recommend the starting point is the iStructD's guide on how to calculate embodied carbon. That's definitely a very sort of comprehensive but broad enough view so that anyone with an engineering background can start approaching this if you're coming at it from zero. Then linked to that on the right-hand side is a screenshot of the guidance note that we published within the Net Zero Bridges group and is now available on the website in draft form. So this is up there for people to log into and use, and it specifically covers bridges. So there will be parts that obviously, and if you're writing a guide trying to cover all structures, you can't go into as much detail. So this one here tries to pick up and fill in those gaps, but follows the same framework as this. And then the 2 on the left are, I guess, even another higher level above. So it's looking at calculation methods for construction works in the standard here, which is sort of, again, sitting a level above this and setting out an overall framework. And then PAS 2080, which I'll come back to, because this standard is linked with management principally, but as part of the management, you need to have the calculations done with the appropriate sort of boundary conditions and things so that it's compatible with how the guide works. So that's another important reference. So now we've got the details under the way. Let's have a look at some bridges. So starting with the one that's the bridge that's in the cover photo for this presentation is Duke's Meadows Footbridge. That's a design we've been developing within Covey in collaboration with Moxon Architects for Knights Brown Construction on behalf of London Borough of Hounslow. That recently opened the public earlier this year. And what I've got here is a snapshot of the carbon that's in that final design, estimated with as much accuracy as we can from what we know of the as-built information. We can come back and dive into more detail if people would like, but given that we weren't able to have full sight of all aspects of the material supply, we still had to make some assumptions even at the end of construction. But that's this here is a sort of an overview of our estimate of carbon in that bridge, and highlighting up the top, total, we're talking about 600 tons of carbon in the total bridge, and then normalizing per meter squared of the deck area, sort of talking about 1.7, 1.8 tons per square meter. And then you can see it broken down by material and then by life cycle group at the bottom here. So that's one bridge. Let's bring in a few more to get a bit of a feel, I guess, for what we're talking about when we start talking about carbon in bridges. So I mentioned, we're operating in tons. This here I've gone up in a log scale, so 100,000, 10,000, 100,000 plus, and put a few Covey bridges on there, just so people can get a feel of what I mean when I'm talking about total carbon. Looking at these from left to right, there's a pretty obvious sort of link between them that's sort of, or proportionality that's leading to those increased values. It's the size. So obviously we're starting at the left, it's clearly the smallest bridge, it then has the smallest carbon footprint. You step your way up, you can see, we're going into the medium to large scale, we're starting to get to generally bigger bridges. I guess the use is also changing, but I'd say when we're looking at total carbon, that's not really going to have too much of a sway. It's really, we're talking about overall size when we're looking at total carbon. And that's a theme we'll come back to when we start looking at how to manage carbon, is that overall size. So to pick out one, a few here on the far left is Floral Street Bridge in London, in Covent Garden. Over on the right is İzmit Bay Bridge in Turkey and Mumbai Trans-Harbour Link, both very big bridges. So then how do we compare bridges between each other? And I think I sort of alluded to it the previous one. We need to normalize. The functional unit that we will generally normalize by is the functional deck area. So if we do that, we can have a look now and have a look at the carbon intensity or the normalized carbon in those same 6 bridges. And I might just toggle backwards one more time. You can pick out one or two and follow it on to the next slide. You can see some of them almost completely swap. So Mumbai goes from the far right to the far left, and Floral Street goes from the far left to the far right. Picking out those in a bit more detail, the cross-section or the span arrangement for Mumbai Trans-Harbour Link adopts consistent repeated 60-meter spans for almost all of the crossing. So once you start to normalize, because you've got a repeated structure with a highly optimized cross-section, it follows that you're getting quite an efficient or a low carbon intensity out the back. Looking at Floral Street, in this case, that was because of access and abilities to maintain, that's manufactured with aluminium, and it has a very high architectural finish because of what it's connecting and who the users are. And then when you normalize per meter squared, it then gets penalized. And interestingly, once you look at it in this frame, it actually ends up about similar to İzmit Bay Bridge. Now sort of touching a little bit on the ones that stay about the same, I guess just to pick out İzmit Bay, and the link there is that once you normalize, you can then start to look at things like what does span do to the carbon intensity? What influence does the primary construction material, the primary construction method start to have on these type of designs? And I guess a common thread that we've found is that there is generally a proportionality between span length and carbon intensity to a point. Obviously, you get to a point when you start to get the really small spans that, depending on other factors like material choice, it may then start to sort of buck that trend a little bit. But now we've sort of introduced 2 key themes I'm going to come back to: total carbon and normalized carbon in bridges. And for all of these, just to link back, this is A1 to 5 carbon or upfront carbon. Before we can start to look at how low we can go, I think any sort of good engineering problem needs to understand its boundary conditions. So in here, I've pulled out just the sort of 3 common uses that we will normally build a bridge for, being for pedestrians and cyclists, highway bridges or roadway users, and for railway. And then I've also lost a 0 on the bottom here. We are talking a whole order of magnitude less at the boundary condition, starting from absolutely nothing, a nature path that's just sort of carved out. Obviously, there's nothing associated with it. As you start to then build something for people to use, you then have some emissions associated. And these numbers here I've pulled out from some data available online, and then also just from some high-level hand calcs for carbon per meter squared. So what I guess the numbers to keep in mind is that, for the footpath, we're sort of saying 10 to 150. The highway sort of 50 to 200, the railways 150 to 400. And I've normalized them by meter squared again, just to keep it consistent. I will side note here that normally for roads, they're normalized per lane per kilometre, and for railways, just per kilometre of track length. But for the purposes of comparison, have tried to approximate them to a metre square normalized parameter. So that's the lower bound. The upper bound are these big long span bridges, right? So we touched on a little bit with Isma Bay. This here is a feasibility study that we looked at for a connection between Scotland and Ireland, going back a couple of years now. And these type of bridges, they're set the upper bound. And the idea of presenting this is, again, to sort of put boundary constraints on what we're looking at in terms of a problem. And I think, again, going for a quick side note, I will point out that these type of structures, what it means when we bring in carbon into the criteria to decide whether to build them or not, is that it just provides another metric to make sure, as a community, that the investment is worth the reward. So there's that extra economic layer that particularly gets more complicated with these big bridges, and that's definitely a topic for another presentation. But for now, I guess the upper bound is, right at the top, sort of 5-6 tons per meter squared are these sort of mega long span bridges. Now that we've covered the sort of calculating of carbon in bridges, how are we going to manage it? I think it would be no presentation on management of carbon in bridges without deferring to PAS 2080. For anyone that has sort of seen this before, this is the latest version that came out in April this year. And this process flow diagram sort of summarizes the overall intention of the standard. And hopefully I'm not going to lose too many viewers by deferring to this standard, because I will admit, the content is a bit dry, but the importance of standards like this can't be undersold. So written in a way that gives a client a route to procuring low carbon is very important, right? So this standard, I think, balances the sort of need for it to be possible to write into a contract and for it to be written into clauses and things like that. It balances that side very well with acknowledgement that projects have their own constraints, and that, setting targets and how often it's monitored and assessed. I'm talking about carbon in bridges, how often that's monitored and what scope you consider. That is up to the user to define. So it gives you the framework and the tools, but I think, as I say, it doesn't tell you how to do everything. It sort of allows the project to respond based on the constraints that it has. And that's why I think it's particularly useful. And then just to highlight what we're talking about here, what I've spoken about in those previous slides is assessing carbon or calculating carbon. And then the main outcome when it comes to management is integrating that into decision making. And that's what the PAS sort of keeps at its core. And that's, I guess, where we'll get to in these next few slides. So then once you have assessed your carbon and you're looking at your project, how can we then look to reduce it in a sort of systematic way? And that's where something like this carbon reduction hierarchy can step in and help. There are a few sort of different iterations of this, and I will acknowledge that the latest version of PAS has slightly different wording to what's here. This one here is again taken from the iStructG's content, and I think quite well links in from an engineering perspective what we can do to minimize carbon. And it follows, under the use less stuff banner, which I think Will Arnold is sort of turning towards use less new stuff. We're talking about build nothing, build less, build clever, build efficiently, which are also what was in the previous version of the PAS, and then minimizing waste. And I'm going to step through these in a bit more detail in the next few slides. Then just before doing that, just having a look at some of the references. So the PAS is on the left there, which I spoke about. And I guess that the key thing is that it sort of adopts a systematic approach to managing carbon in any infrastructure or building project. And it is, definitely worth considering. And as I say, the strength in it is that it's auditable. It's possible to write into contracts. It can genuinely make a positive outcome when it comes to procurement. It does, though, leave a gap on the technical side. And that's where things like the Design for Zero guidance that the iStruct put out helps to plug that gap from a technical point of view. So once you have a target, how can we sort of answer some of the technical questions around reusing existing material and, ensuring we have the most efficient load paths and things like that. And that's where Design for Zero is a very good starting point for anyone looking to sort of step into or is trying to systematically consider the technical reduction opportunities on projects. Coming back to our reduction hierarchy and talking about in a bit more detail, this diagram, I appreciate, comes up in many forms, and generally this sort of similar trend is the same with cost. But in terms of carbon, our biggest influence is at the beginning. And the first questions we should be asking ourselves is, can we build nothing? Is maintaining something that already exists an option? Is the route really needed at a system level? Those sorts of things. They're the sort of questions we're talking about, which in some contexts will, you could dismiss them within 5 minutes, but in others, they're well worth investigating. And it's just, again, in this hierarchy, we should be taking the time to pause and ask that question. Once we have to build something, then we need to think about what's the smallest thing we can build. And at this point, I'll revert back to that previous slide about total carbon, where there's a clear link between the size of the bridge that we're talking about and the total carbon that's in it. And that's something not just from COVI's bridges, but from other net zero bridges group members. That's a clear conclusion that we're seeing. And a good paper on that is one by David Collins, if anyone's interested in reading that. However, let's have again, another little side note on when would it not be appropriate to build less or build nothing? Just again, to make sure that when we're approaching a design, we're choosing the right thing. So this is where we start to look at that network level impact of bridges within the transport infrastructure context. And I've got two examples here that I'll spend a little bit of time on. So starting with the left, I've picked a spot randomly from a satellite image in South Australia. Obviously, the users on the roads will be very different in this place versus where this sort of consideration might be more important. But the geometry of it works quite well. So let's say we want to get from A to B as part of a new transport link. But we have this extra geometry where depending on the alignment, it does also influence the bridge length. I'm obviously simplifying a lot of other aspects that will go into choosing the appropriate alignment. But for the purposes of managing carbon in bridges, you can see that for a certain point with a certain number of expected daily users, there will come a point where it may not take very long for the average traffic emissions associated with users of that bridge to offset or to sort of, offset the increased capital carbon that the bottom option might have. This here is the quickest route, has the longest bridge. So this generally you would expect would have the higher carbon of the alignment options. So I guess the point here is that at that network level, there are considerations where sometimes going with the shortest bridge that may take a longer alignment might not be the right decision for that whole life carbon sense. And again, caveating that carbon is one criterion within a broader set. So that's that one. Then if we look at more of a mode use or a mode shift type view, on the right-hand side, I've got a photo here of the cycle snake in Copenhagen, where you can see that it follows this lovely S-shaped curve, and it is a great bridge just in terms from a structural engineering point of view and detailing. But in terms of the alignment, the sort of smooth S shape is clearly not the 100% shortest way to get across the obstacle. But by making the bridge slightly longer, it increases the usability from a cyclist point of view. And then with that sort of mode shift in mind, you can, from a transport network point of view, directly support more people cycling. which may be replacing driving, taking public transport or something else, but it supports that more sustainable mode shift. So that's where sometimes building something bigger may actually end up with less carbon. Those cases aside, we will now look at, when we sort of set the bounds of our bridge, how can we look to build clever and build efficient? So now we're sort of operating the next level down. We're saying we've got our alignment, we've got our sort of total bridge length-ish defined. This is where something like this rating system that David mentioned in the introduction can come in. It gives, and I'll introduce a bit of the background, but the article's there and linked if anyone is interested. But it was developed with myself and Dan Green, taking a lot of inspiration from what had been done for buildings, in the sense that it provides a sort of very clear, very intuitive rating system that immediately alerts the user: are they doing well, or are they, is there a constraint there that's driving a carbon outcome that should warrant a bit more investigation? That's what this rating system is trying to do. It's trying to help people baseline. It's trying to help people, achieve lower carbon outcomes through a sort of easy to understand metric. So on the left-hand side, this is the same number we were looking at before. This is that kilos of CO2e normalized per functional square meter of the deck, with a nice sort of colored rating that matches what you might see on your white goods, and increasingly getting used in more applications. And this, in terms of the carbon reduction hierarchy, as I say, we're talking clever and efficient now. So we've got the total length. The stages of a project where this will come in probably influences more of the people on this call, in that it's where we will generally spend more of our time when we're starting to develop a concept, we're starting to develop the design, look at the detailing, how it's going to be built. That phase in the middle there is where this sort of system can really come in and help support decision making. I'm going to pull a few threads together here. So we're going back to this normalized carbon in bridges to understand the background for the rating system. So what we're taking here is each bar within this plot is one bridge, and the value on the left-hand axis is that kgs of CO2e per meter squared. And we're talking about A1 to 5 carbon for the bridge divided by the functional area of the bridge deck. So that's this carbon intensity and this normalized carbon in bridges, which we sort of touched on a few slides ago. So scanning your eye across all these bars, you can see we've also got the structural system there, but you can see the range we're sort of looking at. It's sort of 1 to 3 tons. There are some that go above, sort of 4 tons. There's a couple of big ones there. And then there's also a couple of small ones, sort of that sneak underneath that trend. And I'll get to those in some of those in the last portion of the presentation. The last one on Scorbs and how it can influence carbon management is that it is sort of set up so that at the time when we put it together, the average carbon intensity of the bridges within the COVI database was at a D to E boundary. And it was set up so that there was room to go down and to measure if something's more carbon intensive, but also gives plenty of scope to go up, with the idea being that by 2030, average or minimum target, we're looking at a B. You remember our average coming out of a bridge office or a portfolio is B, and then towards 2050, A+, getting down to as low possible carbon as we can. So with that, I can now, I think, pull everything together and answer the question that you've all come to see. How low can we go? This here I have specifically focused on current practice, and in the Q&A we can certainly pick up on what that might look like in the future. I'm very happy to take input from others, particularly if you're more familiar with some of the decarbonisation route maps that are out. But this here is looking at current practice. So starting with a footbridge, the example I've gone with is Hampton Footbridge, which I have spoken about a couple of times previously, just because firstly, it uses the rating system exceptionally well. But secondly, with having adopted an A+ as the aim, within the sort of conjoint design team of engineer and architect, this here is a COVI and Moxon design development. And with that early establishment of the target and the same team being kept from a similar scheme previously, they were able to look at the previous one for a similar bridge and take all the lessons learned, adopt a target from the outset, back when the design was just a line on the page of a possible crossing. So they had a rough total bridge length and they had the alignment. Then they said to themselves, we've just done a similar bridge. Let's see how low we can go. And they've gone for the A+. And at the moment, the scheme is depicted on the bottom right with the main span across the river. In this image, you can see the short approach spans. At the moment, that bridge is coming out about 450 kilos per meter squared. And that's something that is a rolling number that's being assessed as the project progresses. And some of the sort of technical outcomes of trying to pursue that are detailed in a case study on the Net Zero Bridges Group website. But it's all around absolutely maximizing the efficiency of material usage, looking at the alignment, which is taken to minimize pier heights. It was also done to reduce the bridge length as much as possible and the size of the abutment required. There's a set of stairs here, which doubles as a lateral brace for dynamics. There's lots of things which I suppose, from a technical point of view, you could certainly say is just very good engineering. But the extension with a carbon view is that you can then see what you're coming out with and use that to influence how you're progressing. Underneath the pedestrian banner, we also had a set of the Bridges to Prosperity quantities for one of their bridges. And I thought, for fun, for this presentation, what do they come out as? For anyone that's unfamiliar with Bridges to Prosperity, they're a charity that build rural footbridges in developing countries. And the particular focus here is a bridge that they built in Rwanda with, I think this one was a Bechtel bridge for the quantities that we had available just from searching online. To pick out some of the aspects here, the B2P team, to make these as economic as possible, they reuse almost all the structural material that's used for what you can see in this bottom photo. So the main span cable is recycled from a crane. The steel decking is recycled from either, a temporary works from building situation or any other sort of previous building application. The mesh comes secondhand. I think in terms of the only new materials, what was actually governing this was the cement that they use in the foundations at the end, the abutments for the concrete, and then the diesel that they use on site. So their current practice from our sort of rough calcs that we used, they're coming out about 420 kilos per meter squared, which actually surprisingly is not too far off what we're looking at for Hampton. But if we were to apply some of the other things that we would then put on for bridges here, if we then looked at maximizing cement replacements, obviously, again, another sort of side note that the cement replacement is a sort of another whole discussion onto itself. But just for the way of saying how low could this one go, if we looked at cement replacement in a similar way to what can be done for bridges here, if we also sort of surmise that perhaps they could use solar voltaics for 90% of their power on site, still leaving 10% of the diesel, and then used recycled rebar from a similar source to European suppliers, it actually gets down as low as 190 kilos of CO2 per meter squared. And a nice example. But I think if we come back now, obviously we have our pedestrian bridges, but then what about a road bridge? How do we stack up when it comes to getting as low as possible on a road bridge? And I already mentioned previously the Mumbai Trans Harbour Link, which is also a very sort of strong contender for setting this lower bound for a highway bridge. But at the other end of the scale, I've picked out Honey Monster Bridge. So Covey Bridge finished, I think, midway through last year or year before last. This is again a Covey Moxon Bridge for Knights Brown. And this one here, taking the embodied carbon A1 to 5 for this bridge, comes out at 840 kilos per meter squared, resulting in a strong A in this Sculpt's rating system. Then what about if we jump up another step in the scale? So the last one here that I wanted to talk about in terms of new bridges is Thames Valley Viaduct on HS2. This here is definitely at the other end of the scale of some of those smaller bridges that I've just talked about. I think it's 880 meters long, two tracks of high-speed rail line for HS2. This scheme here is currently being constructed at the moment, and again adopts this mantra of absolutely minimizing material use as much as possible from the top down. And also there are some sort of extra benefits in that minimized waste category with the large scale precasting that's being done. So then this one here comes out at about 1.3 tons and gives you a sort of a very strong performing B rating on the scale with the details here. Again, picking out some of the aspects of this, the sort of project specific title that I've put on that previous marker, that's adopting sort of expected average concrete mixes with 25% GGBS over the structure, and it adopts the UK CARES average for embodied carbon in reinforcement bar. I think one interesting point to highlight here is that this is a series of short spans, repeated, again, highly optimized cross-section. The substructure is actually the higher component than the superstructure, which is not generally all that common. As the spans start to get smaller, obviously the substructure has a larger proportion of the total carbon. This one here partly linked with, or mostly linked with, the ground conditions. But I guess one interesting side note that came up from this study. But obviously these are all new bridges, and I've probably given it away a little bit, but the lowest carbon bridge is obviously one that already exists. So this here is Clifton Suspension Bridge, and it follows on from a study that we recently finished and wrote about in the iStruct about what the user associated emissions are with that. There's a bit of information in there on some of the key conclusions about managing maintenance and what that does to traffic, but focusing more just on the sort of more pure structural engineering point of view. In terms of maintenance, this comes out to about 3 to 4 kilos per meter squared per year of embodied carbon from what we had available as the sort of long-term asset owner, which again, in the context of getting to 2050, if we sort of say, about 25 years, that's 75 to 100 kilos of CO2 per meter squared that gets you to 2050. I guess bringing it back into aligning with roadmaps, at a broader industry level, that then aligns with when we should have available lower carbon materials, lower carbon processes, all those sorts of things. And just, I guess, flips around the context a little bit as to how we can think about keeping what we already have going as long as possible. Then the last slide from me is really to open up and ask for people to share. So I've presented a series of COVID examples on low carbon outcomes, but I would be extremely interested to hear from everyone else. How low can you go? And what are your minimum carbon outcomes? What some of the key decisions and constraints that allowed you to get to very low outcomes? I think, this sort of, it's an industry-wide challenge, and I guess sharing best practices is the core of what we're trying to do at the Net Zero Bridges Group. So certainly you've got the links there to reach out to us. Outside the bridge sphere, for people that in more just the general structures space, there's the iStruct, which I've mentioned a few times, and then also through the IABSE with the symposium that David mentioned. And at that symposium, we're hoping to host a special session from the Net Zero Bridges Group, where we'll have the chance to open up to everyone in the room and hear about some of the things everyone else is doing. So with that, we'll end it there. Thank you very much.
Thank you, Cameron. Fascinating, as always. Just a reminder to the audience, please put your questions into the Q&A box at the bottom of the screen, and we will do our best to answer them collectively. Cam, do you want to stop sharing your screen for now, and we'll nip straight in? Great. Picking up on some of the questions that have been asked, a key criterion, and we discussed this briefly before, is how the work that we do as bridge engineers interacts with what that infrastructure is facilitating. And I've got two questions really here that address that. One of which is, in the operational phase, the bridge will attract more traffic. Does it mean that life cycle carbon will increase? And then secondly, for a road bridge, wouldn't the emissions from users during the bridge life be more significant than the ones required during construction? How are they estimated? Do you base it on traffic usage over bridge length, or increase due to the bridge, or maybe take into account some reduction due to a shorter route created? That's a big question, and perhaps is something that you can talk around briefly.
Yeah, I'll try to pick out a few aspects. I think I'll probably start with the easier one about should we be thinking about it. Definitely the answer is yes, and I hope I haven't tried to divert any attention away from considering that. One example that I would go to there is the work we're doing for Lower Thames Crossing, where within the sort of whole life carbon view, it includes the impact to traffic during construction, and it also has a model that predicts the road users in the future, and also tries to capture the influence that by having a more efficient route to cross the Thames compared to existing M25 crossings, what that then does to increasing potential road users in the future. That then gets into a whole sort of next step of questions. Well, how do we bring in that, there's anticipated that traffic will decarbonize in the future as well. It's a tricky question, and I think it also comes back, certainly with a UK context in mind, I think to challenging ourselves a bit more as to say, do we really need this now? Can we avoid it or put it off? And I guess that's the sort of view where the Welsh Authority came from, where they put a big pause on a lot of their road projects. Again, I'm touching on lots of things that could easily fill a whole nother hour. But I guess within our bridge sphere, and something that PAS 2080 encourages is that, we shouldn't just operate in our bubble. We need to be aware of those full, value chain decisions and how we could potentially influence them. Then once we get to our sphere, we then need to make sure that we've definitely got our house in order. That's obviously the focus on capital carbon and upfront carbon.
Yeah, as you say, a sort of complex area that we can only touch on here. A couple of interesting questions here on the reliability, I suppose, of the data. Firstly, to do with as-built information, as the design team target versus an as-built completed scores rating, and keeping a record between the two. Firstly, is that something you've done? Secondly, is that something you'd support? And then secondly, more generally about auditing values and the potential for greenwash in the values that are suggested.
Yeah, very good questions. So I think it's definitely something that I would support. I think the projects we operate do have quite long time cycles. So sort of integrating this into the full delivery of some of our projects does take a bit of time to just work its way through the wash. And again, deferring to something like Lower Thames Crossing, the contractor is obliged to measure their emissions during construction. And it's through those sorts of things where we'll start to be able to really rigorously check as built against design. The example that I was able to touch on in more detail was Duke's, where we did have a good, as accurate a go as we could do with the information we had to include as built information. On that one there, I would just say, it wasn't a written in contract requirement. So it's harder to get the information when it's not sort of written in as a formal requirement. But I think we need to get that data in to then calibrate what our design decisions are. And I think this is also linked with something we try and touch on in that calculation guide, is that we need to be a bit careful on finding an environmental product declaration for the lowest possible steel and saying that's what we'll use to give us a lower rating. I think we need to be using averages until we are guaranteed that we have a certain supplier with a certain embodied carbon factor. And that then helps, that greenwashing approach, I think, in a big way.
One of the suggestions made has been about auditing in the same way that you might do an independent check, and not just checking what's been done is accurate, but also perhaps suggesting areas where other things could be investigated or addressed. Yeah,
it's something we sort of kick it around. I've seen it written into things like the concrete route map, low carbon concrete group route map, where they talk about the independent check being expanded to be not just is it safe, is it efficient, as setting like both bounds. I think there is a lot of merit to exploring that. I think what we need to do, certainly we need to be aware that as a client, from their point of view, sometimes consultants, we do just like to potentially get into discussions that might not help their progress. And I think that's the balance that we need to strike. We need to be able to provide commentary as a checker to say, is there excessive material use? But I don't think it has benefit to start arguing about, second decimal places and utilizations. I think that's a waste of time.
Interesting question here on how we share these emissions. Can you typically share the carbon emissions for a bridge between all the companies involved? Is there a way of dividing it up like that, or is it purely on a project by project basis? If a company wants to report it as part of their carbon footprint, for example.
Is this around like how you break up, in what you're assessing?
Well, what are you responsible for as an engineer? We often talk about, if we design a more efficient steel frame, we will save X. But how is that divided between you as the structural engineer and the contractor and the fabricator and the architect?
Yeah, I would say that the best way to sort of integrate carbon into what we do is to put it within the scope of the person responsible for deciding how big it is, basically. Has the responsible for the size, the finish, the specification, the responsibility to calculate carbon should sit with them. If it doesn't, which may well be the case on a bigger project, you might have a specialist team that's sort of pulling in quantities from everywhere. That the responsible person or discipline lead needs to get the feedback in, I guess, the most efficient way possible. If they're getting what carbon's in their design or their part of a design after the drawings are finished, it's too late, in my opinion.
I think sort of in addition to that, the question was, well, what are we guilty of as designers? If a client suggests the bridge needs to be 15 meters wide and 300 meters long, is that our responsibility as a structural engineer to take on that carbon cost, or does some of that sit with the client? It's a kind of a leading question because they're different scopes of carbon accounting. But where are the boundaries, and how do we divide up the responsibility for the carbon that we're emitting?
Yeah, that's something that the PAS really tries to take on. Again, putting the primary responsibility with the asset owner. So, in the context, you've decided the asset owner is the sort of ultimate responsible for, I guess, the baseline, and has to be sort of strongly linked with what targets are being set, and getting the reports back of the assessments and things like that. That's where the PAS sits it. I'd say on a day-to-day sense, it sort of does get shared a bit. I think there is that ownership that should sit with the design team to then act as a motivator.
Interesting question here about carbon tunnel vision. How do we avoid it? Obviously, other environmental indicators, EPDs, and some impacts can't be quantified. Biodiversity, impacts on flood areas, and so on. What's your view on the balance of those influences?
I tried to sort of, I guess, touch on it throughout the presentation, that the firm view needs to be that it's an important criterion, but it's not the criterion, and there are plenty of other things that have to be considered. And within a sustainability space, the other sort of two big things that will generally come up is biodiversity and social value. Those ones, I guess, the harder part for an engineer working on the project is that it's a bit less tangible. There's not a direct link to what goes on our drawings to then what happens at the end. But again, at sort of that sort of shared responsibility point of view at the early stages in projects, looking at things like how could we improve biodiversity on the site? What options are available that can engage with local communities better, and those sorts of things. I think that there needs to be space for that. You're right, and I would say that we need to get more mature in terms of carbon assessment, such that it becomes something like a CDM type process, where it's an important part of what we do, but it does get balanced with everything else.
Got a question here on optimization, commenting that on several of your examples as a highly optimized design which reduces the embodied carbon. But noting that in case of bridges that needs change, i.e. the traffic load, this optimization may cost a lot of carbon in the end because the bridge will have to be strengthened. Does it make sense to incorporate that uncertainty, and how do we approach that from a carbon point of view?
Yeah, I suppose it almost could be taken as a philosophical question as to how sort of optimistic or pessimistic you might be about its durability or future traffic. I would say for things being done with current design standards, I think we, as engineers, we need to have the technical skills to be able to go to that reliability limit, which may be, 99% utilization of the design factors that are in the code, or it might be that actually, if you have a specific case where you need to allow for more load, you then do that, but you're not then leaving a gap for like an unknown just to say, oh, it's a sleep at night factor. I think that's where we need to challenge ourselves.
I'd also add that the fact that we may need to strengthen in the future. As humans, we're pretty bad at forecasting what our future usage will be, and there's a danger that we spend carbon for a predicted future that doesn't actually happen, and we do that repeatedly.
Yeah, I guess one more point on that, David, is there is one school of thought that says if we can like push our infrastructure to just get over 2050. Then provided everyone else does their bit, that's the job done. I'm not condoning that's the attitude we should take, but there is a sense that at the moment, whilst steel and concrete industries decarbonize, and particularly from a steel sense, if you talk to manufacturers, they have quite well-defined route maps as to how they're going to decarbonize production. If we can squeeze that bit of extra life to get it there, then actually doing the strengthening in the future, maybe that's not a bad option.
We've got a couple of questions, quite interesting ones on your database of projects and what you've understood from that. One, are there any notable embodied carbon performance trends other than span length, i.e. material choice or total length or area? And then, how that changes for material and whether you've calculated it for maintenance. What impact, what trends are you seeing within that database that you have? It's obviously not public information, but is there anything that we can draw out of that we should be learning about?
Yeah, I guess at a very high general level, if I was sort of tackling a new project, the sort of trade or the transition point for cost between, say, a concrete cross section or a steel concrete cross section, from what I tend to see in the data, that tends to happen higher, so at a higher span length for carbon. So concrete tends to be the more efficient option. Very generally, there are so many caveats, but that's something on the material use superstructure. A concrete cross section in the UK from standard suppliers, yada yada, all that sort of stuff tends to perform a little bit better and push that balance point for steel out just a nudge. Other things, I guess, that we generally notice, span's obviously the one that's, I guess, easy to come back to, and we do influence. Overall size, definitely bigger the bridge, bigger the carbon. Almost always, there has to be some quite extreme scenarios for that not to be the case.
In terms of intensity or the actual numbers?
No, sorry. I was talking total numbers. Intensity, no, I wouldn't say. There's actually, on the data, we see the smaller the bridge, the bigger relative influence the abutments can have, which then depends on how it's interacting with whatever it's around. So if you have big abutments but a short span, your intensity sort of goes up quite a lot because you're normalizing.
Okay. Question here, is there a significant difference in outputs depending on what measure you use? For example, does considering in terms of energy versus carbon change any of your outcomes, or is the accepted method to use embodied carbon equivalents as a proxy for everything else?
That's a good question. To be honest, I'm not really sure. I have seen results from a fully detailed life cycle assessment that considers all the indicators and looks at energy as well. But I don't have those numbers to hand, so I'm not too sure.
One to go away and think on.
Yeah.
And then a couple of questions on how you address this at the early stage. When adopting a rating system and making carbon impact a key influencer, are you seeing client teams proactively adopt this, or are you needing to sell it every time? And when you do that, are you quoting an upper and lower bound in your estimate, or how are you assessing the accuracy of what you do?
Yeah, I think the approach we've sort of found as we start having more and more of these conversations, some of them obviously happen the other way too, where the client will come and say, we want to do this sort of thing. In ones where it is the other way around, almost always at a personal level, there's a lot of interest. I think the discussion normally needs to cover quite early on that by going lower carbon generally also means lower costs, that we're not at the point of specifying some material that costs, an absolute mozza per ton or anything like that. It's more about sort of optimizing processes, which should lead to lower costs. And once you get that sort of covered, almost always that is a good key to unlocking the right discussions, to really getting in and doing it properly. In terms of setting targets, yes, definitely would give a range, especially at the early stages. Things like GI and other things that just tend to come a bit later throughout the process can have an influence on what you're looking at. So yeah, definitely would go with a range.
And I'm sorry to everybody whose questions I haven't been able to answer, but we're sort of running out of time. But one last one, which I think is quite pertinent given some of the images you've shown. How does architectural design in terms of aesthetics and visual language impact the carbon emissions? Do you think that making a bridge landmark or iconic, we need to compromise on carbon emissions?
I wouldn't say compromise. I would say, again, this idea of challenging. So by seeing the carbon that we're doing and the influence that a decision is making, it then needs to feed into what is also a more complicated decision-making process that we'll go through. I think what having a carbon lens will do is focus minds on, if we are going for a longer span, what are the drivers for it? Is it really necessary? Those sorts of things. But I would say that from our experience working on projects, when we bring it in early and engage with it well, the sort of combined, bridge architect team then over delivers, on what you would have started with if you tried to do it by yourself, or if you tried to just say, oh no, we don't want any of this extra stuff because it's going to be extra. In terms of carbon, I think, again, that collaborative approach is the key. And there isn't a compromise, I'd say. If anything, it can add to it, because then you can accentuate where you're trying to save material in a way that then, helps get funding for the project, and all the things that, outside of our carbon bubble are super important.
I think that's a great place to stop. As I said, apologies to those whose answers we haven't been able to answer, but please do get in touch with Cam or myself directly, and we can hopefully continue the discussion. I think your point about getting outside the carbon bubble is vital, but also we need to be recording and measuring these things as a starting point, and the emergency is real, and what we can do as professionals needs to be taken seriously. So thank you very much, Cameron, and thank you all for attending. Superb event, and looking forward to continuing the discussion and seeing what comes out of it. Thank you.
Thank you.